All right, here we go. So we are in section 4.5 on your textbook. Um, you can see here, optimization is a useful application of differential calculus. What that means, it's an application of derivatives. We've been studying derivatives for so long now. This is another application of derivatives. Anytime you use the superlative case, biggest, smallest, cheapest, etc., you are trying to optimize. What is keeping us from making something infinitely large or infinitely small? There is usually some limiting factor or constraint that prevents that from happening. So just like with related rates, we had a set of steps that we would follow for the related rates problems, right? So we're going to have another set of steps for optimization problems. And I know this looks long, but it's kind of like if you're able to do this, then you do it, or you have to do this. So that's why it's kind of, there's a lot of words here for the steps. And the first one, obvious, make sure you're reading the problem carefully and that you're understanding. And I think it can be really helpful, just like with the related rates problems, to draw a picture if you're able to, and to label that picture. Then you're going to want to state what you are trying to optimize. So like whether you're trying to minimize cost, to maximize volume, to minimize surface area. You want to state what you are trying to optimize. So when you're trying to maximize or minimize something, that's when you are trying to optimize. You then need an optimization equation for the quantity that you're trying to optimize. So if you are trying to maximize volume, you need a volume equation that has volume in it, or an equation where you could solve for volume. If you are trying to minimize cost, you need a cost equation. If you're trying to minimize surface area, you need a surface area equation. So you have to come up with an equation that involves the quantity that you are trying to maximize or minimize. That's really important. And we're going to identify, like that has to happen, and we're going to identify that equation as our optimization equation. So then you're going to want to state any constraints. So if one of the variables, like one of the quantities that you label that you're using in your equation has to be greater than 0, you're going to state that constraint, like x has to be strictly greater than 0, or x has to be between 0 and 5. You want to explicitly state what that constraint is. And then you also want to write a secondary equation involving those constraints if necessary. And you'll see what I mean by that. I think our first example is going to have a secondary equation. And if you remember, we kind of had to do that. We had secondary equations when we were doing our related rates problems. When you had an equation that you were trying to take the derivative of, but you had multiple variables that you didn't necessarily have extra information about. So we use a secondary equation to help us rewrite an optimization equation. So that was step 5, right? You use the secondary equation to help you rewrite the optimization equation if necessary, and simplify the optimization equation. I've probably broken these up into more steps than I need to. You're going to take the derivative of the optimization equation and find the critical values. You guys know how to do that, right? Find the derivative, use whatever rules you need to. Find critical values by determining where the derivative is equal to 0 or undefined. And you'll also need to consider endpoints. So those constraints that I mentioned before, which would maybe correspond to the domain of your optimization equation, you need to consider those endpoints. And that's really important. The most important step is step 8, where you're going to confirm that the critical value or endpoint is an absolute max or min using the extreme value theorem implication. So that's if you have a closed interval and the function is continuous, you can make the table and determine what the absolute max or absolute min is depending on what you're trying to solve. Or you can use the first or the second derivative test, which remember is local extrema, but based on those constraints, you're allowed, like the constraints of the problem, you're allowed to just use the first or the second derivative test. Now, anybody who's taking AP calculus, I believe you have to do an extra statement or analysis of why a local extrema would actually be an absolute extrema in that situation. I'll try and give an example. But I'm okay as long as you show the work for like first derivative or second derivative test, usually first derivative test. Then that's enough justification for me. And then you need to answer the question in a complete sentence with the appropriate units. And last step, smile, because you just use calculus to optimize, and you should feel good when you finish these problems, just like your related rates ones. So before I start example 1, does anyone have any questions for me? Okie dokie. Let's do it. So example 1, this is going to seem like kind of a silly problem, but just like related rates, we're starting really simple. And then we're going to work our way up into some more difficult level problems. Okay, so example 1. 2 positive numbers have a sum of 60. What is the maximum product of one number times the square of the second number? So just interpreting that first sentence, 2 positive numbers have a sum of 60. We don't know what those numbers are. We could use any variables we want. We could use like x plus y is equal to 60. And since both of those numbers have to be positive, x has to be greater than 0, and so does y. The thing is, we're able to come up with that equation, that relationship, but that's not what we're trying to optimize. We're trying to determine what the maximum product, right? Product is multiplication of one of those numbers times the square of the second number is. So that means our optimization equation will have to have a product in it. I'm going to use P for product. So taking one number, how about x, times the square of the second number, so times y squared. So those two numbers, when added together, are 60. We know both of those numbers are positive. So our second equation, P equals x times y squared, has the same constraints. That x has to be strictly greater than 0 and y has to be strictly greater than 0. However, this equation with P in it, this is what we're trying to maximize. Therefore, this is our optimization equation. And this first equation that we came up with is actually the secondary equation. And we need the secondary equation here because, well, if we wanted to take the derivative of our equation with P in it, we have X's and Y's. So we would want to use our secondary equation to rewrite in P in terms of a single variable. So we could solve for X or Y from our secondary equation and then rewrite our optimization equation. Are we following what I'm saying? So I'm going to take the secondary equation and I'm going to solve for X. You could solve for X or Y, it doesn't matter. But the reason that I'm going to solve for X is I prefer to replace this X rather than replace the Y and then have to square whatever I would be replacing Y with and multiply that out. It's just less algebra, but either works. So if we rearrange that secondary equation, we would have X equals to 60 minus Y, which then we can take the 60 minus Y and replace that X. So we would have P equals to the quantity 60 minus Y times Y squared. And that's our optimization equation just rewritten. You could take the derivative as is. You would need to use product rule, right? Because the equation is written as a product. I suggest distributing the Y squared in, so we could just use power rule. And then we're ready to find the derivative. So then we're ready to use calculus. So I'm going to, again, pause right there. Does anyone have any questions on any step? Okay, so now I'm ready to take the derivative. I'm going to find P prime, right? We take the derivative of the optimization equation. So that would be 120Y minus 3Y squared. And to find the critical values, our optimization equation is a polynomial. So to find critical values, we can just think about setting our derivative equal to 0 and solving that equation. So I'm going to solve that by factoring out the GCF of 3Y. So what, that would be 40 minus Y then. So our critical values would be Y equals to 3 and then Y equals to 40. But remember up here when we stated our constraints, Y has to be greater than 0. So our optimization equation that we used, Y still has to be greater than 0.
Wait, Miss Dorset?
Yeah.
Why is Y equal to 3?
Oh, I meant 0. Thank you.
Okay.
Thanks, Zach. So we have that constraint on our optimization equation that Y has to be strictly greater than 0 because in the problem we're given that there's two positive numbers that sum to 60. Therefore, 0 can't actually be a critical value. We're able to to throw it out as a critical value. But we also know that y has to be strictly greater than 0. So 0 is kind of an endpoint. We don't have a closed interval that our optimization equation is defined on. Therefore, we're going to use the first derivative test. To identify, well, local extrema, but it'll actually be the location of our absolute extrema given the constraints of this problem. So I make the analysis line. This part's all familiar to you guys. I put my critical value of 40 on there, but I'm also going to put 0 as an endpoint because I can't choose a value less than 0 to test. So then for test values, I could use like 1, and I could use 41. So plugging those test values into the derivative, p prime of 1, I'll use function notation, p prime of 1 would be 120 minus 3, which would be a positive value. So the graph would be increasing to the left of 40. And then p prime of 41, not 40. Well, that would be 120 times 41 minus 3 times 41 squared, which I believe is negative. I don't have my calculator near me, but in my notes, it's showing negative. So since the graph goes from increasing to decreasing at the critical value of 40, and we have the constraint that our product equation, our optimization equation is defined for just y strictly greater than 0. That means on the interval from 0 to positive infinity, the graph will go from increasing to decreasing at one point. So whenever 40 is the input, the question is, what is the maximum product? So it's not asking like us to find the two positive numbers, although we could, right? We could plug 40 into our equation where x is solved for, and we'd know what the two numbers are that would maximize that product. But we're being asked for just the maximum product. So we could plug 40 into our optimization equation, right? 60 times 40 squared minus 40 cubed, and we get 32,000. So the maximum product is 32,000. So if this were a question on the AP exam, you probably need to make an extra statement, like basically writing down what I said, like because the domain for our optimization equation is from 0 to positive infinity, the graph will only change from increasing to decreasing at y equals to 40, and therefore 40 is the location of the absolute extrema. So you just need to do an extra statement. Does anyone have any questions? Okay, so let's try example 2. I'm going to move a little bit faster if that's okay with everyone. So you have 40 feet of fence to enclose a rectangular garden along the side of a lake. What is the maximum area that you can enclose? So we have our lake. That's the edge of the lake. And we are trying to enclose a rectangular garden. So I'm going to draw. Okay. I know it doesn't look like it, but just go with it. These two sides are the same. So I'm going to call each of those sides X. And you might label differently than me. It's up to you how you want to label what variables you want to use. I'm going to call those two sides X and this side Y. And since we're trying to maximize the area, we need an area equation. Well, area of a rectangle, length times width, or in this case, X times Y, right? That would be our optimization equation. But we have the issue that we have an X and a Y in our equation for A, right? A is what we're trying to optimize. A is what we're trying to maximize. So we have to use a secondary equation, right? That's how we know that we need a secondary equation is we have this equation. We're like, oh, okay, we're ready to differentiate, but we have multiple variables in this equation. So can we use a secondary equation to rewrite A in terms of a single variable? Yes. So going back to the word problem, the given information, you have 40 feet of fence to enclose. So that means that each of those sides needs to sum to 40, or the sum of those three sides needs to be 40, right? 40 must be equal to 2x plus y. That would be our secondary equation. And it's probably going to be easiest if we just solve for y. But it doesn't matter. You could solve for either. So then we can rewrite our area equation as x times 40 minus 2x. I would distribute that x in before taking the derivative. So that's our simplified optimization equation. And then we're ready to differentiate. So A prime using power rule would be 40 minus 4x to find the critical values, critical value or values. Set equal to 0. It's again a polynomial. So you just need to worry about setting equal to 0. That's not always the case. And we would get as our critical value x equals to 10. Now, if we think about it, we can put constraints on x. So on our optimization equation that we took the derivative of, we could put constraints. Since we only have 40 feet of fencing, and each of these sides has to be the same length. Well, first of all, if x were 0, then you would just have, you wouldn't have an enclosed rectangle. So I realized that in that case, the area would be 0, but you could technically have area at like, if X were equal to a fraction of a foot. It would be a weird looking fenced in area, but you would technically have area. So we can say that the smallest X can be 0. And the largest X could be is 20. Because if X were 20, then we would just have 2 parallel fences. We wouldn't have an enclosed area. So the enclosed area would be 0, but like we can use that as a constraint in order to have our optimization equation defined on a closed interval. Right, that can also be represented in interval notation from 0 to 20. Does anyone need me to explain that again?
Yes, please.
Yes, please. Okay. So remember how I said, we're going back up here. Step 8 is we want to confirm a critical value or an endpoint as an absolute max or min, either using extreme value theorem. So that's if you have a continuous function defined on a closed interval, or using the first or the second derivative test. When possible, especially if you know the function that you have is continuous, you want to see if you can come up with a closed interval that the optimization equation could be defined on. For example 1, we had no limit to what y could be or what x could be, right? Like we could have actually, because we were given that it was 2 positive numbers, we couldn't even use y is greater than or equal to 0. It would have had it. There was no way to make a closed interval. However, for this situation, if you think about the constraints on x, right? If x is 0, that means there's just one long fence, no enclosed area, but the area would be 0, right? Which it is possible. It's not super helpful, but it's possible. And if x were equal to 20, then you just have 2 parallel fences and still no enclosed area, but the area would be 0, which is possible. So because our optimization equation is continuous and we are able to define on a closed interval, we want to do that so that then we can just make the table with the endpoints of the interval as well as the critical value or values that lie on the interval. And then we're just looking at what gives us the largest area. Well, we know that the area is 0 when x is 0 or 20. And then when we plug in 10, what is that? 200. So 200 would end up being the absolute max. This is the justification for the absolute max. Here, I'll even put a note over here. Extreme value theorem applies. Right? You're guaranteed to have both an absolute max and absolute min. The absolute min here would be 0, area of 0. We don't care about that though. The question is only asking for the absolute maximum area. So to summarize in a sentence, you could say the maximum area of the garden is 200 square feet. Okay, we're gonna go. Actually, you know what? Maybe I'll save example 3 because I've kept you guys here for a long time. Before I let you go, here, let me stop